So hello and welcome to this manufacturing systems technology module 17. We were trying to discuss about the various machining operations as needed in a computer assisted planning process, and in context of that we covered the basic turning and milling operations and also drilling operations in the last lecture. Would like to just review some more processes and then go to the planning approach, or how do you plan these different processes for making an engineering part. So we'd like to start with the grinding operation today. So obviously grinding is more or less like a finishing process, and material removal is achieved in any grinding operation because you have a rotating abrasive wheel which sort of digs into a workpiece, and this abrasive wheel is able to remove very small portions of materials from the interacting abrasive tips with the workpiece surface. So in fact grinding is quite similar to milling, except that an abrasive wheels are used in place of milling cutters. Milling cutter, there is one point at a time interacting with the surface, but in the grinding wheel there are many such points which interact maybe at the same instance of time with the surface. So grinding is generally used to obtain the finest dimensional accuracy, and this was in fact a surface finish process which had been developed for manufacturing products actually. And the common different varieties or the variants of grinding processes which are involved may include surface grinding, cylindrical grinding, internal grinding, centerless grinding, so on and so forth. So the various parameters of surface grinding for both horizontal and vertical grinding cases are shown here in this particular figure. This is the horizontal case which talks about the machining time or the material removal rate in terms of the various parameters related to how the grinding wheel is positioned with respect to the workpiece surface. Okay, and for the vertical surface grinding also the same kind of estimate has been made in this particular figure. The both machining time as well as the metal removal rate is slightly different in this particular case. Okay, and this is only geometrically derived in any manufacturing process technology course. So now let us look at that. Just because we said about surfaces and surface roughnesses, this figure kind of shows an array of different roughnesses where we are talking about average roughness here either in micrometers or micro inches, and as a function of the different processes which are involved in giving this surface finish. So the various processes here, for example flame cutting has been shown to yield a surface roughness between 15 microns, 50 microns all the way to 6.3 microns. Obviously there are certain ranges where you have relatively higher applications. So these black regions here are for those processes where there would be an average application of the process for obtaining the particular desired roughness, and very less frequently the process may be used for obtaining a roughness as indicated by this white region. So obviously the black regions are the one which are mostly the roughness ranges which are covered or which are used to cover by this surface. So flame cutting for example would yield a roughness on an average 12.5 to 25 microns surface average roughness. Similarly the coarse grinding operation or snagging as it is better known would actually yield a surface roughness starting from 25 to 6.3 microns. Similarly sawing can go from 25 all the way to 1.6 microns. It is used even beyond, but then these are the less frequently used regions for this machining process. So a variety of these processes: sawing, planing, drilling, chemical machining, electrical discharge machining, milling processes, and then a variety of other like broaching, rimming, electron beam machining, laser machining, electrochemical machining, turning, boring, barrel finishing, electrochemical grinding, roller burnishing, so on and so forth. All these different processes have been given in terms of their average roughness values which would emanate for most of the frequently used applications. Okay, so that's how the manufacturing processes are classified. So once you have this data of surface finish, you can see or plan even hybrid process sequences where in an assembly operation you may need a lower surface finish. For example, there may be a super finishing need of the range of about 0.2 microns or so, and you may need to use some of these like polishing, lapping or super finishing on the top of some other machining operation which has been made earlier. Okay. So this is how you actually find out the different surface roughnesses obtained from the different manufacturing processes. So what really is a process planning? When we are talking about different products and their components, they are designed to perform certain functions. Mostly these functions are in assemblies, so assemblies of the different components. So the process planning is really about how you can choose a sequence of processes so that an engineering part or a group of engineering parts goes into assembly operation, so that they can be enabled to function as an assembled product, assembled final product. So it really acts as a bridge. The planning really acts as a bridge between the design and manufacturing, by translating the different design specifications which have been arrived at in the design phase into manufacturing process details. And therefore it is nothing but a set of instructions which have to be done to enable the right choices in the processes and the right choices in the sequence of the processes, so that the particular tolerance in the design or the particular measurement in the design can be realized finally in the end product. Following basic steps are needed in developing a process plan. So let us look more closely towards it. So you have a number of activities which need to be utilized, and here there is also an optimization, because there are various choices which come up and you will have to really choose the correct path or the correct sequence. So the first step is the analysis of the part requirements. Then you have selection of workpiece, raw workpiece, that means material selection step, determining manufacturing operations and their sequences. Most important step. You have the selection of machine tools. So selection of tools, work holding devices, inspection equipments, and then finally determining the machining conditions. For example, cutting speed, feed, depth of cut, so on and so forth. Manufacturing lead times, which include setup time, processing time, lead time, so on and so forth. So there is a series of these activities which are involved in developing of a manual process plan, and then we will later on see how we can computer assist this, and in what kind of decision making algorithms would be utilized when there are several choices and there is an optimization route that is followed to pick up the appropriate choice to do the correct process sequencing. So let us look one by one on these particular issues, what really we mean by analysis of part requirements. So the primary purpose of a process plan really is to translate the design requirements for parts into manufacturing process details. So at the engineering design level, remember we had a design process or design thinking earlier, where we talked about how you can design various engineering products. The part requirement can be defined as part features, dimensions, tolerance specifications, etc. And we have to convert them into processing requirements. That is the whole reason why analysis of these part requirements are carried out in a very, very appropriate and very, very detailed manner. Now let us say you consider this particular example, that you have a final part to be made of this type, shown here in the part E, and you consider the part to be coming out of a block, which is given in the part in the figure A, okay, with plain geometric feature. So therefore the part is successively modified. The first instance you actually put a step in this particular region to the part, then probably you put a slot somewhere here. So the step is already existing, carried to the step C, you put a slot somewhere here, and then obviously there is a side step which you try to take from this particular area off, and then finally you put a blind hole somewhere here throughout the block, okay, to realize the final part, blind cylindrical hole with two steps, one flat step and a side step and a slot in the same particular block. So this sequence of operations, that what proceeds what, is nothing but a sort of intelligent approach looking at the various machining concepts which have been described before to the requirement, the engineering requirement to realize the final geometry or the three-dimensional geometry from the solid block of the material is being considered. So this analysis process of the requirement of the engineering design, obviously there has to be a feature size, there has to be a tolerance size, there has to be a basic dimension, there has to be a process capability. These aspects have to be considered when we talk about such analysis for part requirements. So this is step 1 of process planning. The step 2, as we indicated, is selection of the raw workpiece. So basically the raw material is very important. Not only that, can I optimize the machining time, select something. For example, let's say you had just seen in the last step here that the product at E finally emanated from a block at A. So how do we assure that this block is just of the size where minimum machining is carried out to achieve this? Obviously there has to be a profit angle in all organizations when you try optimizing the manufacturing processes. So therefore the correct raw material size and shape, for example, is it a billet, is it a block, is it a flat sheet, is it a cylindrical bar, what exactly are we using, what shape we are using as a basic raw material, so that with minimum amount of machining you would be able to have your final engineering parts, is of a very importance, a very perennial question. Okay, so that's one part that we need to have as far as the selection of the raw workpiece is concerned. And then obviously the economics of manufacturing would determine the overall required oversize of the raw part, okay, so that you can remove minimum amount of part to create the engineering part in question. The weight of the material of the raw part obviously are dictated by the functional requirements of the parts also, and things like, for example, what is the type of the material to be chosen, whether it can really take up the ultimate yield strength or performance which is needed for that particular engineering part while in assembly or while in a machine. These aspects also come to the stage of selection of the raw workpiece or raw workpiece material. So once that is defined, then obviously the manufacturing operations and their sequences need to be planned. So that's the next logical step in the process planning, determining the appropriate types of processing operations, their sequence to transform the features, dimensions, tolerances of a part from the raw to finished state. There may be several ways to produce a given design. Sometimes constraints such as accessibility and setup may require that some other feature be machined before the others. I just showed you one example before where we talked about what is this, the different processes involved here. For example, let's say in the block you first carved out this particular step function, right? This step. This must have been done by some kind of a face milling operation or something on this, or maybe even a combination of just a shaping process with respect to a grinding process as a hybrid, and then you considered doing this particular slot, okay, and then a side slot. So had I done the side slot earlier and then started working on the slot, it may not be a very appropriate mechanism, because the slide slot then in that case would have to go for a greater amount of depth, and the material would have to be subjected to a tremendous amount of shear stresses and strains in comparison to if you had already created this step. So there is a sequence in which you have created the side step with respect to the whole step here in figure B of the part requirements. So there is obviously a basis for the sequencing of the different operations. Sometimes you may talk about holes, or you may talk about corners which are inaccessible when another machining process is worked upon it. Okay, so can I have the accessible part first, and then later on when we have already assembled it, the inaccessible later on, so that one part which was not accessible in the assembly stage is accessible at a component stage. So some of these are really very important considerations to determine the sequence of the processes while doing process planning. So there can be some other questions asked, for example, whether a process plan is optimal on a 3 or a 4 axis machine, and whether the same plan can be on a 5 axis machine, okay, because of the greater flexibility of the higher axis machine. So if such a thing exists, then can we combine these requirements which could otherwise have been generated on a 3 or 4 axis to a 5 axis, so that it has an additional compatibility to develop something more to the same part if need be at a future change of design of the particular part. So these kind of things are also a part of the manufacturing operations and their sequences. And the surface roughnesses and tolerances, particularly as a design requirement, also influence the operation selection. For example, let's say a part requiring a hole with low tolerance and a surface roughness specifications would require a simple drilling operation. Now the same part with much finer surface finish and closer tolerance requirements would require first a drilling operation, then a boring operation to obtain the desired surface roughness, and then the tolerance of the whole feature on the whole feature of the part can be realized as per the design. So these are some of the basis of finding out what are the manufacturing operations and their sequences. So having done that, the next step is the sequence of the process. I'll just illustrate two example problems here. In this one example problem, how will you, for example, realize this part? So it's a combination of various cutting motions. There may have been a block of this sort, a solid block, out of which probably there has been some milling, angular milling, which removes material in this particular zone or this particular zone, and there has been also a drilling, as you can see here. So if I were to precede the drilling by the milling process, meaning thereby that, let's say, the milling has been done and then the drilling is being performed. So is it a good option? The answer is no, because obviously drilling on an inclined plane is much tougher than drilling on a surface. For example, if the block were solid and the milling had not been done and the drilling took place from that particular surface, so that later on obviously the portion has been angularly milled, that would have been a much better operation. So the drilling coming first in this process followed by the angular milling is something that is engineering, which gives engineering sense or engineering logic for handling this part. For example, in this particular part, again you can see that in the hole H2, this particular hole must be produced before machining the slot here, because otherwise if you produce this hole after the slot has been cut, there is a chance of this section to bend and it may actually deform. So therefore determining such manufacturing operations sequences is very important from the engineering part requirement point of view. Therefore the CAP or the computer assisted process planning should work on such experiential models of determining what comes first and what comes next to determine the whole process sequence, manufacturing process sequence. The other important issue is the selection of the machine tools. So that's the next step in the process planning after the selection of the manufacturing operations and their sequences to and their sequence. Now you have to select the machine tools on which these operations can be performed. So a large number of factors would influence the selection of a machine tool. For example, workpiece related attributes such as kinds of features desired, the dimensions of the workpiece, its dimensional tolerance, and the raw material form. That would be something that is the first need for, or that's the first factor which would influence the selection of the tool. Machine tool related attributes such as process capability, size, mode of operations, whether it is a manual or a semi-automatic or an automatic or a numerically controlled machine, tooling capabilities such as size and type of tool magazines, etc., or automatic tooling changing capabilities. Those are some of the determinants again for selection of the machine tools. And then finally the production volume related information, whether the machine would be able to give you the particular or meet the production quantity requirements or the order frequency requirements. That is a big issue which needs to be taken care while doing the selection of machine tools. So in a nutshell, we have now covered the analysis of part requirement, that is the first step of the process planning. We have then obviously covered the selection of the raw workpiece. We have also covered determining of the manufacturing operations and their sequences, and then finally the selection of the machine tools. Now we will also try to analyze how this process capability of different toolings can be matched to the specification. We will take a single example of doing the basic turning operation on a shaft, and then try to see how we can do process capability analysis of a machine so that a particular machine or a range of machines can be selected, based on the requirements of the design given in the shaft design. So that will be in the next module. So I would close on this module here by just mentioning that process planning obviously is the intelligence of the operators who are actually associated with processes for longer amount of times as read in a very organized manner. And then the engineering design to part, what are the bridges which need to be sort of covered, is what the process planning is, or is really what the intelligent process planning would be all about. Okay, thank you.